In the part 1 of Ordinal Logistic Regression video, we learn how to use this regression when we analyze outcome variable, which has 3 categories in order. In part 2 of this chapter, we are going to use this model to analyze skewed continuous outcome variable. This study is one of my collaborative studies. We are analyzing effect of having ApoE4 gene on prolonging delirium days in ICU. So we measured patient cognitive status every day during patient were in ICU, and we counted number of days where they were observed with delirium. And we want to compare distribution of delirium days between 2 groups, one with ApoE4 gene and one without ApoE4 gene. Usually variables involving days are highly skewed because it can't take negative value and then usually few patients with having long days. Okay, therefore analysis is challenging. If you analyze this data with student t-test, okay, and clearly it violates assumptions, right? Because student t-test requires normality of outcome variable within each group of patient. And as you see this data, but let's go ahead to do student t-test because many people actually do use student t-test. And we know that's wrong, but let's see the result of t-test. And first you look is p-value for equality of variance is significant or not. If it's not significant, p-value is greater than 0.05, and you look top lines for your result. So p-value will be this one instead of this one. Its p-value is 0.433, so that indicates there is no association between ApoE4 gene and total number of delirium days. And you know student t-test is wrong. So what is the better alternative here? So let's perform non-parametric test. And non-parametric test, when you have continuous outcome variable with 2 groups, is Wilcoxon-Ransom test. In SPSS, we call it Mann-Whitney-U test. And this is a distribution-free test. So if you go ahead to do Mann-Whitney-U, and the p-value is 0.015, and therefore using non-parametric test, we found association between ApoE4 gene and duration of delirium. And so, if you finish your analysis with Mann-Whitney-U test and write up your paper and submit, what very likely happening is reviewer come back and say, well, this is not RCT, so we can't really guarantee equivalence in 2 comparison groups. So the result can be confounded, and therefore please redo your analysis by adjusting for potential confounders. What analysis we should do then next? So we know we can use regression and we can account for confounding variables in the analysis. But challenge here is what kind of regression we can do. Since you have continuous outcome variable, duration of delirium. So how about to use linear regression and transforming outcome? We know data is skewed this way. It has large cluster at minimum level, 0 days of delirium, especially among patients without ApoE4 gene. No mathematical transformation provide normality with the data in this type because all you do is just shift the distribution and then you cannot get rid of cluster at minimum value. And how about binary logistic regression? Now we can create new variable encoding 1 for patient who has at least 1 day of delirium and code 0 for patient with 0 days of delirium. So let's perform binary logistic regression. So first we are going to categorize delirium days into a binary variable, and let's do that in SPSS. Okay, so to compute a new binary variable, you go to transform compute variable and let's call it okay, and so when the expression in this box is true, and this will return 1, otherwise it will return 0. Okay, so if you click OK, and let's make sure. So when delirium days is 0, it returns 0. When delirium days are greater than 0, and it returns 1. Okay, so new analysis, we will use this binary outcome to do logistic regression. So go to regression binary logistic and put this new variable under dependent box and put ApoE yes no in covariate. And ApoE yes no variable is binary variable coded as 0, 1, so we don't have to worry about pushing this categorical button. So let's click OK. So odds ratio is 3.361, so it indicates increasing odds of delirium by having ApoE4 gene compared to not having ApoE4 gene, although result is not statistically significant. So let's discuss why we did not observe statistical significance when we use this binary outcome variable. Okay, it's because we lost the information, and we originally knew exact number of days of each patient having delirium, although after we record 201, and we no longer know this patient has 3 days of delirium or 10 days of delirium. So it is a huge loss of information. Loss of information often leads to loss of statistical power. What is statistical power? Probability of detecting difference when there is a true difference. So here I conducted actually some fun simulation on statistical power. Okay, so what I did is I generated data from 30 data points, 30 patients, and I set Pearson correlation being 0.5. Okay, right? So this is a scatter plots of the data. So I conduct some fun simulation, and as I wanted to see impact of loss of information on statistical power. So first I generated data from 30 patients, okay, on their BMI and cholesterol. And I want to examine association between BMI and cholesterol. Okay? And Pearson correlation coefficient is set to 0.5. And since many people doesn't understand what correlation coefficient mean, so what those people do instead is divide patient into 2 groups based on BMI. So let's say this case median BMI is 25. So they divide it to below median and above median. So we have non-obese versus obese group, 2 groups. And then compare mean cholesterol level between non-obese and obese. And analysis choice is student t-test. Okay? And some people even don't understand meaning of mean, but they understand proportion. So instead of plotting mean of cholesterol level, and they plot percent of cholesterol higher than median. So they dichotomize outcome variable and exposure variable. And at this stage, people start calling you dichotomania. And so now let's see statistical power for each analysis. So what is the power again? Probability of detecting difference when there are is truly difference. So of course you want to have higher power. So this simulation, I set the power to 80% or greater. And student t-test, where you dichotomize exposure variable, power become 59%. And the last test, chi-squares test, when you dichotomize both outcome and exposure variable, and the power is 12%. So even if your data is telling you there is true association, the chance you detect the association is only 12% because you conduct wrong analysis. So when no mathematical transformation provides normality in residuals, the use of linear regression is difficult. One way to deal with a situation like this is to categorize skewed continuous outcome variable into categories. Many people categorize it into a binary categorical variable, but we need to remember that fewer categories are, less power become. Ordinal regression, proportional odds logistic regression model, is in fact heavily underused. In papers published in the BMJ, JAMA, the Lancet, and the New England Journal of Medicine during 1991 to 1994, only one paper used the proportional odds model for ordinal response. The other 100 articles use binary logistic regression. So this is a shocking news. So those 108 analyses, and then many of them could detect statistical significance. But I'm sure those studies suffer by loss of power because of loss of information. So using this data of delirium days, what should we do? We know we can't. How about 3 categories? Let's put it in 3 categories. So there is very useful option in SPSS, and we can create tortiles based on continuous data. So you go to transform, rank cases, okay, and we want to transform delirium days, okay, and we go to rank, and here we want to have 3 categories, so put 3 and continue. Okay, so go back to data sheet, and now let's make sure I have 3 levels. So 1 goes delirium days. Let's compare with this one. Okay, so 1 new variable, total of delirium days is 1 when delirium days 0 and 1. Okay, and then it is 2 when delirium day is 2 or 3, and then delirium day 4 or greater is put in the category of 3. Right? So now we have 3 categories. So let's use proportional odds model. Okay, so to do proportional odds model, you go to analyze, regression, and ordinal. And outcome variable is this newly created total variable for delirium day, and exposure is ApoE for yes, no. And this is a binary variable coded 0, 1, so I could put it in factor box, but it's easier to put it in covariate. Okay, let's go ahead to click test of parallel line. This we need to check assumptions. Continue and OK. Okay. This is the result of proportional odds logistic regression. And since this doesn't have automated options to convert beta coefficient to odds ratio, so we need to do that by hand. So where you want to look is this last line. Okay, beta coefficient for ApoE for yes, no. And if we go back to lecture note, we will exponentiate, okay, and then odds ratio is 5.41, And similarly, we do the same for confidence interval. So you can compute odds ratio and 95% confidence interval. So what does this mean? What does 5.41 means? So many people ask. I know this is odds ratio, but odds ratio of what? So in data, we began with 3 category outcome variable. And one day is from actual delirium day of 0 and 1. And level 2 is for actual delirium days 2 to 3 days. And level 3 is delirium days 4 days or greater. Right? And then we have 3 category. And since we cannot really compute ratio based on 3 category, and then we collapse 2 categories together, okay, using each available cutoff. So here we are drawing a line. We're cutting between 1 and 2, so we combine 2 and 3 together. And so after we combine 2 and 3, this become 25, this become 11. So this gives new 2 by 2 table. Based on this 2 by 2 table, and when we compute odds ratio, and that is 9.68. And let's do the same thing. And here, and we collapse 1 and 2 together. Okay, so use cutoff between 2 and 3, and 1 and 4 together. 1 and 2 together. So you combine 22 and 14, and 1 and 4. So that provide this 2 by 2 table. And odds ratio for this is 4.582. And since it's hard to show both odds ratio in the paper, by the way, if you cut your outcome between 1 and 2 days, odds ratio is 9.68. But by the way, if you cut between 3 and 4 days, and odds ratio is 4.58. That makes story too complex. So why don't we pull and just show one result, one number for the result. And when we pulled odds ratio is 5.41. So that's what SPSS computed using ordinal regression. So the last one is checking assumption. So if we can satisfy the assumption, then we're done. So checking assumptions, you click this called test of parallel lines. You click on output. So this is the option. And continue. Okay. So this is the result. And if the p-value is greater than 0.05, that's what we are looking for. Okay. So that suggests assumption, proportionality of assumptions are met. That means those two odds ratios are not statistically different. Okay, so we can finish our analysis. And again, proportional odds model is regression. So if you want to adjust for other variable, and you can do that. In fact, ordinal logistic regression will run with the original continuous variable. Let's see what happens when you don't categorize the outcome variable. Okay, so let's go to SPSS. So here we use ordinal regression with original delirium day variable. And I put ApoE for yes, no in covariate box. Okay, and let's go ahead to click option, output, test of parallel lines. So since we have many levels of outcome variables, we have delirium day, 0 day, 1, 2, 3, 4, 5, 6, 7, 8, 11, 18, 22 days. And we have many intercepts in this model. And you don't worry about these intercepts, and you look at slope, which is beta coefficient for ApoE, yes, no. And you take exponential of beta coefficient, and that provides odds ratio. And this is a p-value for the effect of ApoE for gene. Okay, and let's go back to the lecture note. and exponential of 1.357 is 3.9. So odds of having greater days of delirium is increased by 3.9 fold if patient has ApoE4 gene compared to without having ApoE4 gene. So what this odds ratio means is the model will evaluate odds ratio based on 2x2 table from every possible cutoff variable, okay, and pulled all those odds ratios, and then by average you observed odds ratio of 3.9. So model will run without problem even when you have many categories, and even some categories you have very sparse data, but that is okay. And then if you want to adjust for other covariate, and you can start putting those in the model. So in SPSS, and you can do this very easy. So this is a cohort study. So the result we saw may be confounded by patient baseline severity of disease. So let's put the severity score of Apache. Okay, and Apache is continuous, so we put it in the covariate box and click OK. So now the effect of ApoE4 gene is adjusted for Apache score. So you can include as many as covariate you like in proportional alt logistic regression or ordinal regression, although the number of covariate you can include in the model is limited by total sample size. So linear regression, we divide total number of patients by 15. Logistic regression, we divide minimum of events or non-events by 10. Cox regression, we divide number of events by 10. And for proportional alt logistic regression, and we unfortunately have that easy computation, so you need to go through this messy formula. And it's not as bad as you see. So let's check it out. N is total number of total sample size. And the same here. And NI is number of patient within each outcome category. And so this whole part is summation of cubic of number of each outcome category. Okay? And you compute this whole thing out and divide it by 15. So this is the last slide, checking assumption. So when you check test of parallel line, so now p-value is less than 0.001. So this in fact is a problem. Okay. So null hypothesis for this p-value is all the odds ratios when you cut any possible value. All the odds ratios are the same. So when you reject this null hypothesis and you are indicating at least one odds ratio is different from another. And when that happens, and we see the violation of this assumption, so we may not be able to use this model. Although mathematically, okay, the odds ratio you are seeing here, 3.9, is numerical average of those odds ratios. So that meaning is not changed. So the problem is odds ratios are numerically different by choosing a cutoff. So that's the difficulty using proportional odds model for continuous outcome variable. So in this case, we categorize into 3 categories, and if we already observe statistical significance, we might present 3-level outcome rather than original continuous outcome variable.